So can you see my screen or?
I'm saying, yeah, now it's visible. Yes.
Okay.
Yeah, so I think we can start. It's time.
Yeah, okay.
So welcome you all who are in the virtual mode with us to this lecture series on various topics under the banner of Math Clinic India. Today's lecture is going to be, sorry, just a minute. Yeah, something went off. Yeah. So today's lecture is by Dr. Soumya Day. He is currently a postdoctoral fellow at the Institute of Mathematical Sciences, Chennai. Dr. Soumya earned his PhD from IISER, Mohali, Indian Institute of Science Education and Research, Mohali, in 2018. And he did a postdoctoral position at IISER, Bhopal for about a year. And then he joined Indian Institute of Mathematical Sciences and is there still. So his areas of research is geometry and topology, especially the theory of mappings, mapping closed groups of surfaces and some generalized braid groups. Today he is going to talk about on something very elementary to start with. That is the notion of distance, an overview. So I will hand over the screen to Dr. Soumya. Please, Dr. Soumya.
Yeah, thanks a lot, sir. It's good to talk here in Math Clinic. So my talk will be very basic to start with. It's not for any experts out here. I'll be defining basic things. And if you are an undergraduate student in mathematics, most probably you have come across all these notions. So my audio is clear, right? Can you hear me clearly? Okay.
Yes, very much.
So let me start. So the first thing that we will start with, you consider the line, okay, the real line. Everyone has seen this. So on line, how do you make sense of distance between 2 points? Say if you have two real numbers, say 2 and 5 in this case, okay, in this picture. So what is the distance between 2 and 5? How do you calculate? You basically take the difference, right? 5 minus 2. And then maybe if 2 minus 5, you take mod. So you take the positive value of the difference between two real numbers. So this is how we see that, okay, 2 is 3 distance apart from 5. Okay. Likewise, we have distance on the plane also, right? We all have seen in our schools that given any 2 points, say you take 1, 3 in Euclidean plane or R2, and you take 4, 2, say. Then how do you calculate the distance between these 2 points? You take basically this, right? You consider the difference between the first 2 coordinates and take square. And then you take the difference between the second coordinates and take square, and then add, and then take root. So what this number will give us? This is basically, if you plot, say this is our 1, 3 here in this plane, red dot, and this is 4, 2. Okay, you basically join these 2 points by a straight line, and this quantity, this whatever you get, say root of 10 here, this is basically the length of these line segments, right? This is how you measure or make sense of distance between 2 points in R2. We have already seen all these things. So now let's go a bit deeper. So how do this expression or the expression of distance between 2 points in R2 come? Okay. So we have something called the dot product in R2. Okay. So given 2 points, say x comma y and z comma w, you basically take the product of first 2 coordinates and the product of second coordinates and then add them. So this is the way we define the dot product of 2 points in R2, right? And this is basically an inner product. So in more general settings, this is called an inner product on a space. Okay. Now, using this inner product, we can define something called the norm of a point. Okay. Suppose you have some point x comma y in R2. What is the norm of R2? This point xy. You basically take xy comma xy, this inner product. Okay. And how do you calculate again? X times x plus y times y. This is basically x square plus y square. So this is giving us a norm of the point xy or the vector xy. And now finally, how do you define or come up with the final expression of Euclidean distance between 2 points, these two xy and zw? You basically take the norm of the difference of first coordinate, comma, the difference of the second coordinate, and take the root, okay, to the power half. So this will give us basically the expression we usually encounter. Okay, this is our Euclidean distance on R2. Great. So you can see that all these notions can be generalized to Rn. So n-dimensional Euclidean space also. You can define what is called dot product. So basically, you take, say, you take product of first coordinates and then product of second coordinates, product of third coordinates, and product of nth coordinates, and then sum of all. This will give us dot product.
Soumya?
Yeah, hi.
Somebody has put in the chat box, which is right. Your norm of xy.
Okay.
That square is equal to x square plus y square. On the left hand side or right hand side, you should have square root to be consistent with your later thing. This distance from 0, 0, right?
Right. Okay.
Yeah.
I see. Yeah, exactly. So norm, if you say norm is the distance from 0, 0, then here itself it should be root.
Yeah. So this equality, yeah.
Okay. Okay. Thanks.
Please continue.
Yeah. Okay. So the same definitions can be defined in case of Rn also. Okay. So now, what would be a generalization of this concept of distance in case of Rn? Suppose you have any set X, okay, which is a non-empty set. You can define a function d from x cross x to R, and you call this a metric on X if the following conditions hold. So what are these conditions? So for any two x and y in your set X, you say that the distance or the d of xy, this should be a non-negative real number. Okay, it can be 0 or positive. The second condition says that if you take d of xy equal to 0, this will be only possible if x and y are basically the same point. If x and y are not equal, then this is always greater than 0. Okay. The third condition says that if you consider d of xy and d of yx, these are basically same, right? So basically, when we consider distance from x to y, this is basically same as the distance from y to x. Okay. And finally, the fourth condition would be, this is called the triangle inequality. What is this saying? So if you have 3 points on your plane, say x, y, and z, then you take any of these. So say you start with d of xy, this should be less than equal to dxz plus dzy. And we say that this is the triangle inequality. So such a function from x cross x to the real line is called a metric. And this pair x comma d is called a metric space. Okay, let's see some examples. So we have already seen examples of metric spaces, right? These Euclidean spaces R2 or Rn, all of them with the norm or the absolute value, this will be a metric space. This is example of metric spaces. But there are more. Okay, let's look at the first example in this page. So on R2, you can define a map, say D1. So you have 2 points, x, y, and zw, right? You define them as this. So you take mod of x minus z plus mod of y minus w. Okay, so you can check that this will also give a metric. Okay, all those 4 conditions will be satisfied by this function also, d1. Same as this one. So if you consider on R2, say d2 is the function now. You take xy and zw. These are 2 points on R2. You consider the maximum of x minus z mod and y minus w mod. This will also be a metric on R2. So we have at least 3 metrics on R2, right? One is the usual Euclidean metric. The second one is this D1, and the third one is D2. Now, a good way to see how exactly these three metrics or distance functions are like, what is the difference between them, is by looking at the unit circle in these metrics. So what is the meaning of unit circle in this case? So in R2, you have the origin. Okay. Now, in each of these metrics, you consider all points on R2 such that the distance from this origin is 1. Okay. So we know that for the usual metric or the Euclidean metric, this is basically this circle, right? This is called the unit circle, right? But what about the other 2? What about this inner square? Can you see that this is basically an unit circle with respect to one of these metrics? And if you can understand this, which one of these is it? Like it is the inner square? Is it with respect to D1 or D2? Can you write in your chats? Yeah, some people are writing D1. Okay. Yeah, I think most of you agree it's D1.
Most of the people have agreed.
And what about the outer square? It's with respect to D2. Great. So now you know how these unit circles in these metrics look like. Let's move on. So this is another type of matrix which can be defined on any set, any non-empty set X. You can define what is called a discrete metric. Okay, we are calling it D0. So how is it defined? So you take X and Y in your set, any set X, and you say D0 of XY is equal to 1 if X and Y are not equal. For any 2 not equal elements, you say the distance is 1 in between them. And if X equal to Y, then the distance is 0. You can check that this is giving you a metric on this set, on any set, on any non-empty set X. Okay. So I have put a question for you. So suppose you consider this set. So you have A, B, C, D, E. There are 5 elements in this set, and you put this discrete metric. Now the question is, how many elements in X are within distance 2 from A? Can you write in chat? Yes. How many elements are there within distance 2 from A?
Some people have said 4.
4. Okay.
Some had said all.
Okay.
That is 5.
Okay.
Yeah.
So some people initially said 4, but it's actually 5, because given any 2 point, the distance can be maximum 1. So within distance 2, all of the elements count, and of course A is always there in distance 0. So yes, the answer is 5. Great. Let's move on. Now, so here we come at the, like, what exactly is the main motivation behind this talk? So we have defined what is a metric on a set, and we have seen examples. There can be many metrics, right? On a given set, there can be many metrics. Now, why a metric is very important? Okay. So according to me, so this is the one of the most important notion, which is defined based on the notion of metric, and that is called convergence of a sequence. Okay, so I'll show that using this notion, almost all other notions in metric space theory can be defined. Okay, so let's start with the sequence. You all know what is a sequence, right? So it's basically a map from the natural numbers to, say, R, okay, or any metric space X. For example, let's consider this real sequence, say 1/2, 1/3, 1/4. The nth term is 1 by n. So now it's easy, or those of you who have seen this, so this converges to the point 0. Okay, but what is the meaning of convergence? Let's recall. So given any epsilon positive, there exists a natural number n such that for all n which are bigger than this particular n, the distance between 0 and xn is less than epsilon. So what does it say? Okay, so it says that given any epsilon, so whoever gives an epsilon to me, and I'll be able to choose some natural number n always, such that after this n, whatever small n you take, the distance between xn and 0 will be less than epsilon. So basically, you take a neighborhood, epsilon neighborhood around 0, and almost all, like after some finite stage, all elements of the sequence will be inside this neighborhood, right? And you can choose this neighborhood to be very small, however small you like. So this is the notion of convergence. Okay, so we say that in this case, the sequence xn converges to 0. Okay, and write this. This is our notation for xn goes to 0. Now let's use this notion to define other concepts. Okay, so we will start with the most fundamental, or the second best fundamental concept in metric space theory. So a set A in X is said to be closed if any sequence xn in A converges to some point A, and then A should be in A. Okay, so you take any sequence, it may be convergent, it may not be convergent, but if it converges to some point in X in the bigger space, that limit should be inside A, right? I'm sure you have seen many other definitions of closed sets, but I have just given this definition to show you how convergence of sequence can be used to define a closed set. Okay, so let's take some examples. So what are some examples of closed sets? The first example that comes to my mind is 0, 1 closed interval in the real line. This is closed. You can take the whole real line itself. This is also closed. Or a bit interesting would be you take this 1 by n sequence, okay, the set of all 1 by n's where n varies over natural numbers, and you also put the 0 because it's the limit of this 1 by n. So you can check that this is also a closed set in R. What are some non-examples? Okay, you can take open interval 0, 1. It's not closed because you can choose this 1 by n sequence, right? This 1 by n sits inside open interval 0, 1, and it converges in R to 0, but this 0 doesn't belong to 0, 1 open interval, right? So 0, 1 open interval is not closed. What about Q, the set of all rational numbers? This is also not closed. Okay, so how to show this is not closed? Any ideas? You can write again in the chat quickly. How do you show that Q is not closed? Some people who have not responded, please respond. Let's take, say, 15 seconds. Okay, someone is saying that you take all rational numbers less than square root 2, and then square root 2 will be a limit point. So you're basically taking minus infinity to square root of 2 open, and this set has a limit point. So yeah, so basically you can have a sequence that converges to square root 2, but square root 2 is not in Q. Yeah, right. The second one is also good. So you have the irrational number E, and you can consider a rational sequence that converges to E. Okay. So yeah, all of these are good examples. Great. So Q is not closed. Now, using closeness, we define what is an open set, right? A set A is said to be open if the complement is closed. So you see the whole, these two definitions, closed and openness, can be defined in terms of convergence of sequence. And what are some examples of open sets? You can take open interval 0, 1, the whole real line, or say union of two open intervals. What are non-examples? Again, you can take these, right? So closed 0, 1 would be not open. Q is again not open. Okay, you can check. Any finite set would not be open. Any finite non-empty, sorry. Great. So, right, let's move. The next notion, which we all know, is a continuity of a function. Okay. So you take some function between two metric spaces, say xd and yd prime, and then this function f is said to be continuous at some point x in capital X if for any sequence xn which is converging to x, the image of this sequence also converges to the image of point x, right? So if xn goes to x, fxn should go to fx. So this is a sequential definition. Again, using convergence of sequence, you can define the continuity of a function at some point, and then you say that a function is continuous, then in case f is continuous at each point, right? Right, let's not go over this basic stuff. Okay, so the next concept which we will talk about is completeness. Okay, so a sequence xn is called a Cauchy sequence, Okay. If given any epsilon, there exists a natural number n such that for all mn greater than n, the distance between two elements xm and xn, this should be less than epsilon. Again, it's similar to the definition of convergence, but it's different. Okay, so again, you are choosing, or given any epsilon positive, you can find some natural number n such that any two integers which are bigger than this capital N, and you consider the corresponding terms in the sequence, the distance would be less than epsilon, right? So eventually they're being very close. So a metric space XD is said to be complete if every Cauchy sequence in X converges to a point in X. So, okay. So you take any Cauchy sequence, it should converge to some point. In that case, we say that this metric space is complete. What are some examples? Easy examples. Okay. Again, if you take the whole real line, it's of course a complete metric space. What about closed interval 0, 1? Okay, you can check that this is in fact complete. What about 0, 1 open interval? This is not complete. Why? Because again, you can take this this sequence 1 by n. This is a Cauchy sequence which sits inside 0, 1 open interval, but this is not convergent in 0, 1 open interval because the limit or the limit of this sequence is not inside the set 0, 1. It's outside. So it's not convergent in 0, 1. Same for Q, right? So this example is already, I guess, someone gave. You consider this sequence 1 plus 1 by n to the n. This converges to E, but again, this is not in Q. And you can check that this is actually a Cauchy sequence of rationals. Okay. So this is completeness. Again, we have used convergence of sequences to define it. The next concept that comes in this picture is compactness. You say that a subset A of X is said to be compact if every sequence in A has a subsequence converging to a point in A. Okay, you consider any sequence Xn, and it should have some subsequence. Subsequence means you consider some of the terms of this sequence, some infinite number of terms, and that will be convergent to some point in A. Every sequence must have some such convergent subsequence. Right, someone is writing all these examples hold true. Let me check. Okay, yeah, we can discuss this. So what are some examples of compact spaces? For example, you can again take closed interval 0, 1. This is compact. You can take 1 by n and then union 0. This is also compact. What are some non-examples? You can take whole R, or say rationals, or 0, 1 open interval. All of these are not compact. Now, we have two questions here. So give examples of closed sets which are not compact. Can you quickly answer this in the chat? I need an example of a closed set which is not compact. Great, R equipped with the discrete metric. I guess everyone will be able to prove this, why this is not compact. Any other example? What about R with usual metric? That's also right. That's also closed but not compact. Great. What about the question number 2? Give examples of compact sets which are not closed. Any takers for this? Of course, Sorry, any example of a compact set which is not closed? Anyone?
Not yet.
Not yet. Great. Because it's not possible. Okay, let's come to the theorem we have. So Heine-Borel theorem says that a subset of R, say A subset of R, is compact if and only if A is closed and bounded. So if you have a compact set, it must be closed. Okay, in R. And in general, in any metric space also, this is true. Compactness implies closeness. So you can't find such a set which is compact but not closed. Great. So by bounded, I mean there is some real number, and you can, if you take the open ball around any point, okay, with that radius, it will every other point will be inside that. You say that bounded metric space. Okay. What about connectedness? Okay, so XD is said to be connected if for any two closed sets A and B in X, if you write X as a disjoint union of A and B, this will imply that either A or B is empty. So it's not possible to write the space X as a disjoint union of two closed sets, right? Non-empty closed sets. So what are some examples of connected spaces? You can take any open interval or a closed interval, or even semi-open, semi-closed intervals. You can also take the whole real line or a singleton point, only one point set. This is also connected set. Some non-examples, if you take clearly some disjoint union of two open intervals. This is not connected, right? What about Q? Q is not connected, right? Again, you can choose that example someone gave. You can take square root of 2, and you take all rationals less than square root of 2 and all rationals greater than square root of 2, and these two will be closed sets, right? So Q can be written as union of two closed sets or two open sets, right? What about this set? So take 1 by n and with 0. Is it connected? No, right? So this is a fact that any subset of R which is connected, if and only if A is an interval. So only intervals in R are the only connected sets or subsets of real line. So you see, in this definition also, we have used closed sets, and this closed set we have defined using convergence of sequence. So all these notions till now, we have only exploited the convergence of sequences in metric spaces. The next notion that I'll discuss is path connectedness. So given A and B in any metric space, someone is saying, please explain more of connected set. Okay, so yeah, so basically this is let me again say the definition, what exactly this is saying. This says that if you can write your set as a disjoint union of two non-empty sets, such that both of these A and B, these non-empty sets, both of them are closed. Okay, if you can write, then this is not connected. Okay, it's not possible. It's the definition is saying that if such a disjoint union is possible, then it is not connected. Okay, right? You can see that all these intervals, and you take any interval, you cannot write them as a disjoint union of two open sets, right? So these are examples in real line. Okay. So the next notion is path connectedness. How do you define it? So you have, suppose you take 2 points A and B in your set, okay? A path from the point A to the point B is a continuous function, gamma, from this closed interval 0, 1 into your space X, such that gamma of 0 is A and gamma of 1 is B. So this gamma is a continuous function. We have already defined what is a continuous function. In this case, 0, 1 has the usual metric, and X is given to be a metric space. So you know what is the meaning of a continuous function, right? From a metric space to a metric space. What we want the initial, so the image of the initial point of this interval, the first point, 0, this should map to A, and the image of the last point of this interval, the end point, this should map to B. The image should be equal to B. Okay, if such a continuous function you can find, you say that this image, so you see, you have this real line here, okay, and you have this 0, 1 closed interval. You are mapping it to this curve. So say this is in R2. You have 2 points A and this point is B. So this, if you map this line as this curve, this is basically giving you a path from A to B. Correct? So any such map, or the image of the map, you can say, is a path in your metric space. Sorry. I'm sorry. Let me go again. Okay. So now, what do you mean by a path-connected metric space? So a metric space XD is said to be path-connected if for any 2 points, okay, A and B, there is a path in X from A to B. So if you can join any 2 given points by a path, you say that this metric space is path-connected. And it's a fact that a path-connected metric space is actually connected. So path connectedness implies connectedness. This is a much stronger notion. All right. So again, we have used continuous function here, and to define continuous function, we have used convergence of sequence. Okay. So you see why this distance is very important in this case. Okay. Okay. Let me see the chat. Someone asked a question. Can the same set be path connected in one metric and not path connected in the other? Yeah, definitely. For example, if you take the usual metric, any subset of say interval, this is path connected. But if you take the discrete metric, there is no path. Okay, so the discrete metric on say an interval will not give you a path connected metric. Right. So let's move on. So now, using the notion of a path, we will define a metric on a graph. So let G be any graph with weightage on each edge. So by what is the meaning of weightage? It's a weighted graph. So basically, suppose you have such a graph here, as in the picture, okay? And on each of these edges, I've assigned some weight or some positive real number. Okay, this is called a weighted graph. So now you can even see these weights as lengths of each of these edges. So suppose this length, this edge has weight 2. So we can say that okay, we can think of this edge to be of length 2. Right? So this edge has length 3, this edge has length 2, like this. So depending on the weight on each of the edge, you say that okay, let's fix that. Okay, this edge has this length, the weight basically. So now if we assume that this G is path connected, so what do you mean by path connected in this case? This graph is connected. So from each of these vertex, you can draw an edge path from any point to any point. You can go via some edge path. Okay. So this particular example that I've drawn here, this is a connected graph or path connected graph. So now what is the aim? I am trying to define a metric on the set of vertices of this graph. So as of now, there is no metric, right? Only there are some weights. Now, how do you define this metric on the vertices? Suppose you take some V and some W from your graph, and you define this thing. So what is this saying? So you consider, say for example, this is one point, one vertex, right? This bigger circle that I've drawn here. Say this is one our V, and this is our W. Now I'm trying to give or define a distance between these 2 points. Now what I'm doing, I am finding all edge paths joining this and this vertex. For example, you can start from here. You can go via this edge, okay, and then this edge, and then this edge. What would be the length? This edge I'm taking, this edge path. What is the total length that I have covered? It's 2 plus 2 plus 3. It's 7, right? But there are more paths I can take. I can start from here, then I can go here, say 2, and then this 3, okay, and then this 3. This is another path joining the same 2 vertices. There are more. So you can go from here to this via this 2, and then via this 3. Okay. There are many other redundant paths you can consider, right? So the idea is what? You consider all edge paths between 2 such vertices V and W and take the least possible. Okay. So the minimum of all these length of gamma, where gamma is an edge path from V to W. So in this particular example, if you take this point and this point, what is the minimum length? Can you see? What is the path which has minimum length? I can see that if you go via this, so this 2 and this 3, this is the least possible edge path length, right? So in this case, the minimum would be 5. So you say that the distance between V and W is 5. And we say that such a metric is called a path metric on the set of vertices of the graph. And this is a very useful notion. And this particular notion of taking all paths between 2 points and then taking the infimum or the minimum length path is a very useful notion in many other areas of mathematics, in particular geometry. So such a minimum length path or edge path is called a geodesic in your space. Okay. So you can see I have used minimum here because in this particular example, there are only finitely many possible edge paths, different edge paths that are possible. But it may so happen that in a bigger space, there can be infinitely many such paths, right, between 2 points. Then you need to consider the infimum, right? I guess all of you know this. So infimum instead of minimum, you consider infimum of this set. And that should exist because all of these are positive real numbers. Okay, great. So we have defined what is a path metric. Now, I'll be defining the last concept of my talk. This is also very crucial in a theory called geometric group theory. So let me define what is this concept. So given any group, I guess you have seen what is a group, right? Given any group, you can define a metric on that group. So between any 2 elements of a group, you can define a distance. So how you can do that? So let G comma star be a group, and this S, which is a subset of G, be a finite generating set for G. Okay. So now let's understand what is the meaning of this generating set for a group. Okay. So let's take this example here. Okay. So you start with the group of integers, okay, Z, along with addition. You know this is a group. Now I'm saying that this set consisting of just the one, okay, one belongs to Z, this integer one, singleton. This is a generating set for your group of integers. What is the meaning of this? The meaning is, given any element of Z, you can write that element as a finite sum or finite product, whatever is the operation you have. You can write any element of Z as a finite sum of ones. For example, say 2, you choose 2, you can write 2 as 1 plus 1, right? You can write 3 as 1 plus 1 plus 1. Okay. What about minus 2? Instead of 1, you can use the inverse of 1 also. That is also allowed. So you can write minus 2 as minus 1 plus minus 1. So you can see that any integer can be written as a word. So I am calling this 1 plus 1 plus 1 is a word in this set S. Okay, let's take another example. What about S equal to 2 comma 3? So I'm claiming that this is also a generating set for the same group, 2 and 3. How? See, you can write 1 as 3 plus minus 2, right? What about 4? 4 you can write 2 plus 2. What about minus 1, 2 plus minus 3, like this. So any integer will have some such word in terms of 2 and 3, and you take the addition, that will give you equal to that integer. So you can write any integer as a sum of 2, 3 and their inverses, basically minus 2 and minus 3, right? So we say that this is a generating set. This is a notion of a generating set. Of course, we have seen this is not unique for any group. There can be many generating sets. So let me formally define this. What is a generating set? Each element of G can be expressed as a product of finitely many elements from S and their inverses. If you can write this, okay, then we say that S subset of G is a finite generating set. Oh, finite means it has finitely many elements. Okay, this is the definition of generating set. Let's move. What exactly we're trying to do with this generating set? Okay, so suppose the S that you have chosen is looking like this. So S equal to S1, S2 up to Sn. So n many elements are there in this generating set. So any G, okay, if you choose any small g from your capital G, this G can be written as a finite product of elements from this generating set, correct? So you can choose Si1, Si2, and Sid, t many such words from this set or their inverses. Okay, so in this you can also repeat. So 2, like we have example now, 2 plus 2, you can use 2 twice or more than 1. So repetitions are allowed. Okay, so any such word in these SIs, you can write G as, right? So we have seen again that this is not unique. So you consider for every G, you consider all words in these SIs. Okay, this can be a big set, right? This G can be written as many different words. All of them may be equal to G, right? And for each of these words, you say that the word length of this word. So in this case, we have T many SIs. So this word length is T in this case. Okay. So let me go slow now. So given any G in your group, you want to give this G some length. Okay. You will say that the length of G is some. How will you do that? Okay. So you considered all possible words in terms of this generating set, which represents your word or your element G. And for each of these, you consider their word lengths. Okay. Say W is a word. You consider the word length of W, that is L of W, and you again take the infimum of these LWs. You will say that the length of G is the infimum of all LWs where W represents G. And this will give you a metric on your group. So for each group, you have word length of each element. Okay. So how do you define? It's like a norm, right? In case of usual Euclidean distance, we had norm. So this dW is basically a norm. And then to define any length, so between any 2 points, say you have G and you have H, say, then what is the distance between G and H? You consider GH inverse and you take their dW. So dW of GH inverse would be distance between G and H. So anyway, this has some technicalities that need to be looked at, but the main idea is this. So once you have this dW defined, you can give a metric on your group. So given a group and a finite generating set, you can give this word metric. And as I've said already, this is a fundamental concept in geometric group theory, which is a very promising field, and many mathematicians are currently working in this field. Okay, I'll end with some references. So the first very readable text that I would recommend to everyone is Topology of Metric Spaces. This is a book by Professor S. Kumaresan. If you have not gone through the theory of metric spaces yet, this would be a very good start for you. Somewhat towards the advanced side, I'll have 2 different books. The first one is Metric Spaces of Non-Positive Curvature by Martin Bridson and Hafliger. And the third book I'll recommend is Geometric Group Theory by Drutu and Kapovich. Okay, I think I will stop here. Any questions?
Thank you, Soumya.
Yeah.
I think thank you for starting with a very elementary concepts, which almost all undergraduate students go through, and then coming to some fields of research. So people want to ask questions, you can either put in the chat box or unmute your mic and ask the question, but say your name first and then ask the question. Would you like to stop sharing your screen, Soumya?
Yeah, I can do that. Yeah. So there is one question. Can one find the cardinality of the set of all metrics on a set? Oh, okay, great. Yeah, I mean, in most cases, this is infinite. But I think, yeah, for finite sets also, you can define infinitely many metrics. Because you can scale metrics, right? Once you have some metric defined, okay, say if you have a finite set, okay, say 3 elements, A, B, C, and then you know what is D of AB and D of BC and D of CA, but now you can scale them by any constant C. So you can say that you have a new metric D prime of AB is equal to C times DAB, right?
C needs to be positive, right?
C should be positive. So this will be a new metric. So, but again, yeah, if you have some more criteria on like the scaling, you will say, okay, this is just a scaling, so I will not distinguish between these 2 metrics. Then maybe finitely, maybe I have to check. But yeah, this is a very good question, because for example, say Teichmuller theory. Okay, so what you do is on surfaces, like say hyperbolic. So basically, you consider surfaces, and then you consider all hyperbolic metrics on a given surface. This is a very big space, and you give some equivalence relation between two metrics. And this set is called the Teichmuller space. And this is a very rich theory. Yeah. Any more questions?
Yeah.
Hello, sir. Hello.
Yeah.
Say
I'm
your
Aditya. I'm Aditya. Aditya Jairam. So my doubt is in slide 18, you just defined D of GH inverse to be the kind of distance between G and H, right? So
Yes.
could you define it in this way? Like, D of G and D of H whole inverse. So like take D of G and D of H and just do D of G and D of H whole inverse, like inverse of the metric.
But D of H whole inverse. So D of H would be some integer, right?
Yeah, no, yes, where the metric is mapping to whichever.
Right.
But so that inverse.
But D of something is an integer. So you are taking integer inverse, so 1 by something?
Integer inverse, like no, additive inverse.
Okay. Oh.
Yeah.
Right. So I think that is yeah. Whether that would be fine, right?
I think a simple, straightforward question on the similar line would be: is the translate of a metric another metric?
Yeah, someone said this. So this can be negative, right?
Yeah, that can be. So that is a proper. So
right.
So you can put a mod. Or we can.
Yeah, mod.
Yeah, I think Aditya, you'll have to sit down and check whether those three conditions are satisfied or not. Right?
Okay.
Yeah, immediately one may not be able to sort of verify those conditions.
So you can check that whether D of or dW of GH inverse is equal to what you said.
Is it symmetric, first of all? I think symmetry itself may not be true, what you are saying.
Okay, I will check it. Yeah.
Yeah. No, the symmetry condition probably may not be true. Please check that first. Those are non-negative and symmetry. That is the two elementary conditions to be. Yeah. Anybody else has a question to ask? No, nobody has a question to ask. Soumya, I just want to ask one question which just came to my mind just now, actually, when listening to your talk.
Yeah.
Is purely from the point of view of notion of distance and the real life.
Right.
See, we intuitively, our experience of distance, as you said, basically emerges from the fact saying that the distance between you and me is same as the distance between me and you. So that is symmetry. And distance is non-negative. That is also understandable from the physical world.
Right.
Is there any way of justifying why triangular inequality should be there other than the geometric reason that in the plane it is the two sides of a triangle add up and bigger than third side? So
right.
I just wanted to sort of figure out from the historical point of view or some other way. Yeah.
So there are non-Euclidean metrics also.
No, that's fine. I'm not asking that.
Okay.
if you want to justify, yes, we should have triangle inequality, what could be a motivation uh, for a student who is coming first time? I want to give him some kind of a feel why I should have. One of obviously is that distance triangle. You would have gone through a course in geometry,
Right.
in geometry, and I would say, okay, the sum of two sides is always bigger than third. So there is something carried over to the real line would mean that same thing anyway. Absolute value function has a property. But is there anything else? Have you ever sort of come across some such thing? Why should we have? Other than if we don't have, probably things will go wrong. I know that, right?
Yeah.
Yeah. Probably the convexity of the metric, some other properties.
Yeah. Right.
But
But I don't think, I mean, any other reason that I have come across.
yeah, fine.
Hmm.
Sure.
It's basically, yeah, generalizing the notion.
Euclidean distance from R2.
Exactly. But of course, there are many other geometries. But the definition of metric space, if you remove this triangle inequality, this will be something different, not a metric space.
Yeah, that's right. That's okay.
But yeah, I mean, like other points like symmetry, there are examples of maps which the other two conditions are satisfied, but not the symmetry. So
Symmetry.
distance from x to y is not equal to distance from y to x.
Yeah, that's right.
There are some asymmetric metrics also.
Yeah. If there are no more questions, I would just request all of you to fill up the feedback form. I've already put the link in the chat box. Please fill up that form, and we'll take 1 or 2 minutes. If you can think of some other question or other comment in the meantime, it's fine. Otherwise, please go to that link in the chat box and fill up the feedback form. That will help us to moderate our talks in the future also. That is one. And also, please try to visit the Math Clinic's website, which we had circulated along with the form website link, so that more what is scheduled, what is coming up will be there on that website. So we'll also try to intimate you by emails, but so if there are no more questions, please fill up the feedback form and let me formally thank Soumya for the talk.
Sir, I have a question.
Yeah, good.
My name is Shrigyan. So, you said that a metric takes any value in R, like a metric, I mean, the distance between any two pair of elements of a set takes a value in R. So, can you generalize this?
No, not
in R plus, my bad.
Yes. Okay.
R plus union 0. So, can we generalize this to make it take values in like any ordered field that has a least upper bound property?
Yeah, we can of course define, but we have to see that are we missing out on some of the aspects? Like, can we again, define all these notions that we defined using that concept? So yeah, I need to think on that. It's a good question.
Srigyan, this is a remark for all people. See, generalizations for the sake of generalizations are not always good in mathematics. One can try to generalize, saying that for example, your question that can we generalize it to ordered fields and non-negative values in that ordered field. But what will be the purpose of that? Of course, one is that whether all the concepts, sequences make sense in any ordered field. Limits and everything will make sense in any ordered field. Completeness of complete ordered field, that everything will make sense. So I don't see once you have the notion of sequence and limits and basic concepts true, then there is nothing else which is left for you not to do, right? But what is the aim of doing such a generalization? Do you gain something other than the usual properties or not? So that also one has to, the aim and objectives of generalizations should also be kept in mind in case you want to go in for, in case, I don't know, are you a student or a teacher or a research scholar?
I'm a student.
Right. So in case you are planning to go for higher studies and research, always questions should have some kind of a target in mind that, okay, I'm looking for that kind of property. But I'm not discouraging. I'm just advising you. Okay. So don't take my comments in that way. Yeah. Somebody wanted to ask a question?
Yes, sir.
Yes, please say your name and ask the question.
Yes. Yes, sir. I am Jnaneshwari from Assistant Professor from JB College of Arts and Science, Tenkasi, sir.
Yeah.
Sir, if we take the sir, in the generating set for we take z comma plus. Suppose if we take the operation as multiplication, then we can use the generating set element, inverse of the generating set elements in the operation if we use multiplication, sir.
No, the multiplication will not give you a group, right? Z with multiplication is not a group, because what about, say, inverse of 2? Half is not there in Z, right? So you need to have a group first.
Suppose if there is any other group, we can use the multiplication as an operation, sir.
Yeah. This is so the definition that I have given, word metric. It is true for any group with any operation. Whenever you have a group and you have a finite generating set, you can define.
Okay, sir.
Probably,
for z comma plus.
The confusion came because you said in a general group operation is multiplication, so that is multiplication of. So
Right.
it means multiplication of the group operation.
Yeah.
Yeah, Graneshwari, you wanted to say something more?
Yes, sir. Sir, for z comma plus, we take the singleton 1 as a generating set. Why we can't take 1 comma minus 1 as the generating set?
You can take. You can
Okay,
take.
sir. Okay, sir. Is there any difference between these two sets, sir? So singleton 1 and 1 comma minus 1.
Yeah, I mean, it will give you. So if you take 1 and minus 1, basically the word length will be same, because you're basically putting the inverse of 1, additive inverse of 1 into it. So the word metric will not change.
Okay, sir. Thank you, sir.
Right.
Thank you, sir, for the opportunity.
Yeah, please. Welcome. Anybody else would like to ask?
Sir, another one question, sir.
To
Sir,
me?
in the suppose if we take S as the set with the elements S1, S2, etc. up to Sn, why we are writing the element GS, Si1 star, Si2, etc. Sir, why we can't take S1, S2? If there is any particular reason for this I, sir?
Yeah. So I1, I2, we don't know in which order it will come. No?
And which ones are coming?
I1 can be anything. I2 can be anything between 1 to n, right? That's why I wrote I1, I2 instead of 1, 2.
Okay, sir.
Yeah. So we don't know. Whatever is the word, it will work. Yeah. Any more questions?
Yeah. If not, once again, thank you, Soumya. And
Yeah.
all the participants, take care.